Today's lesson is all about the graph of y equals kx squared, which comes from section 2.5 in our text. You can see we have several different learning goals. We will be talking about finding the rates of change of this new type of equation, identifying the properties, finding out how this is related to the variation equations we've already discussed, and to recognize the different effects of change in the scale or viewing window when we look at a variation equation on our calculator. So before we begin actually talking about the new ones, I want to review with this list some of the characteristics of y equals kx squared. We know it's a direct variation equation because it fits this general equation y equals kx to the n. In this situation, though, we know n is 1. We found it to be a lot like y equals mx plus b. K was actually the constant, which we know was the same as the m value or slope. We know that all graphs of this type will graph into a straight line. We also know that all graphs of this type will go through the point 0, 0. It just depends if k is positive, the graph will be in the first and third quadrants, and if k is negative, it will be graphed in the second and fourth quadrants. Now, these are good beginning to the list of the characteristics for y equals kx. We want to be able to do that same thing with y equals kx squared, which is our new equation in our discussion today. So if you look at this and we say, what do you already know about y equals kx squared? Most of you would probably say, well, I know from previous experience, geometry, algebra 1, that we would get a parabola-like look. If the parabola didn't open up, you would have the same situation, where that parabola would open down. Okay. K is that constant of the variation. K is that value we would always call slope in the previous equation. Question is right now, would it be slope in this equation? So I just want you to think of a bigger situation, so I'm just going to draw one here. And it doesn't matter if these points are positive or negative, so if you're thinking, okay, this is the axis and there's our origin. Whoops, missed the origin a little. Then I want you to look at a few points that we're going to pick out and say, okay, is k the slope of this parabola? We should be able to take any 2 points according to our definition. So I want to take that point right there, and I want to take that point right there. And if we used our definition of rise over run, so we're going to rise up, and we're going to run over, and we would get basically those 2 numbers. Now, that's for any points on this parabola. So I want you to look and say, is the rise over the run in those 2 locations the same if we would have picked maybe these 2 points? Here's the rise, here's the run. Will they be the same? Is the rate you are rising and running the same? That's a key piece to this lesson. And the answer is no. They are not constant rates of change. On the curve, we are getting it going up steeper, so of course the rise is going to be much greater than the run. So we cannot call our k value slope. In this case, it's better known as the rate of change. The rate that it changes in a parabola is not consistent, not constant. Those are 2 things we definitely want to look at. Now, we also want to look at that k value in a slightly different light. So for this, I'm going to a graphing calculator. And you can see the 3 equations that I have used. The first equation is the red one, y equals x squared. Pretty normal. K is a value of 1 in that case. In the second one, purple, you can see we have 1/4 x squared, which in this case the k equals 1/4, the constant of the variation. And the third and final one, I've used a k value of 5. So I want you to look at those relationships and say, what's really happening when I graph those? And you can say, well, they all are parabolas. You can probably say, looking at the graph, they all go through 0, 0. It's definitely true. Those are some of the characteristics that we want to start thinking about and being able to list. But looking at those colors again and the equations, is there a relationship between the k values used in each one and what has happened to those graphs? Because those graphs are not on top of each other identically. They do not all contain the same set of points, and that's key here. What is determining that steepness, the opening between the parabolas, you could say? So if I said, look at that one compared to, oh, and then up here, whoa. Okay, so look back at this. Do you feel anything is true in relationship to the k values and the width or opening of the parabolas? We already knew that since k was 1, they were all opening upward. So that is one of the key characteristics also. But look at the size and look what's happening. And you can even graph one more on your grapher and see if your hypothesis is true. That would be something to do, because that's a characteristic I want you to think about and add to your list that we talk about here before we're finished. So if I have this new equation, y equals kx squared, what are the characteristics? That from our grapher, and now back to our actual sheet. How do we know? What do we know? Your big mini assignment to come to class is, what did you learn about the different characteristics of this equation? What could you list? And I'll go back one slide. Similar to our y equals kx equation, could you do the same thing using all the characteristics from our graphs to make a new list of characteristics for y equals kx squared? And the answer is, of course. Will it have as many characteristics, or some similar and some different? Yes. So when you come to class, we want that list of characteristics for y equals kx squared that you've come up with just by reading. Looking at our grapher, what determines how wide it is, what determines whether it goes up and down, what type of graph is it. Now, one last thing, going back to our calculator model, there is also one other characteristic that we like to talk about, and let's reset our picture here. You'll also notice that the parabolas are graphed in relationship to that y-axis. When you can take a shape and see half of it and identical points, if I just look at the orange on both sides, you know, they have that characteristic where you can look across and see it. You have a low point called something. That characteristic is what you learned in geometry called symmetry. And it's symmetrical to the y-axis. So all parabolas, whether they open up or down, are symmetrical with respect to the y-axis. So a parabola has symmetry, unlike a line. A line did not have the y-axis as its line of symmetry. It does not fold over and make or lie upon itself, make a mirror image of itself. So line symmetry, and it happens to be the line y, or the y-axis, which is x equals 0, remember? So if you want to say our line of symmetry is x equals 0 or the y-axis, that is correct, because the y-axis is actually a vertical line, and all vertical lines are written in the form of x equals a number. So that's definitely one of your characteristics, but see how many other ones that you can add to that list that we just talked about, because that would be the key for class. come with that list of characteristics filled out, and we will see how many characteristics. And just because I have 6 listed doesn't mean there's only 6. I just gave you a few to write. So see how many you can get, make sure they're specific, and make sure they're only for parabolas. All right, we'll check that list tomorrow in class.